And what was the ISC you got? Because to find RTH, according to method 1, VOC by ISC, okay, then you got RTH is equal to 0.2 kilo ohm, because in the denominator you have milliamperes. Yes or no? But the same RTH using old-time technique also let us calculate. RTH method 2. Okay, method 2, old amp method. Okay. According to old amp method, what we are supposed to do? We are supposed to suppress all independent energy sources. Independent energy sources. So when you suppress independent energy source, how the network become? I'm just drawing that network after suppressing the independent energy sources. This is what the network. Yes or no? You draw it, all of you, along with me. Please draw it. One kilo, 2 kilo, 3 VAB, 2 kilo ohm. Okay, this is what you got the resulting network after suppressing all independent sources. Okay, so let me connect now the voltage source according to the procedure V and I. Okay, now VAB will also be equal to V, therefore it will become what? 3 into V. And how these were connected? Parallel. When you have parallel, there is no need to create a variable, just simplify it and you will get 2 parallel 2. It is nothing but 1 ohm. So 1 kilo ohm, okay? 1 kilo ohm. Then that 1 kilo ohm is in series with what? 3V. So if you take this is 0, this is V, then minus I plus V by 1 plus V plus 3V divided by 1. Yes or no? Is equal to 0. Then you can take here 4V and V here. Yes or no, all of you, okay? So what do you get? What do you get here? V is equal to something into I you are supposed to get. Understand all of you, okay? So this is showing clearly that, okay, this is showing clearly that already this is V plus 3V, this 4V plus V, 5V, okay? So 5V is equal to I. Then I is equal to what? 1 by 5. Nothing but what? 0.2 into I. So this is nothing but RTH. 0.2. We are taking kilo ohm because current is in milliamperes. Okay. So you got the same answer, 0.2 kilo ohm in the previous case as well as this case. Okay. Please note down that quickly and we'll move on to another problem. Problem number 15. This was also asked in GATE. The Thevenin's equivalent of the given circuit. Okay. The problem is given like this. Let me draw it once again. All of you finish that. Old-time method is very important. One must be good at it. Because same experience you are going to use in case of two-port networks. There are many problems asked in GATE and other exams, important exams in two-port networks based on old-time technique only. Remember, always remember, wherever the reduction is not possible, not only in case of dependent source problems, sometimes the reduction may not be possible. In such cases, immediately you have to recollect, okay, the old-time method or else VOC by ISC methods. And you also understood old-time method and VOC by ISC methods, where to apply, where not to apply. Okay, so especially when there is no independent source in the given network, the dependent source is dead or inactive in the absence of independent source, then you find current, voltage, power elsewhere in the network will become 0. That we have already discussed. Yes or no? That is why in such cases the VOC by ISC doesn't work. In such cases you have to go for full-time technique only. Now let us look at question number 15. So this is what actually is asking with respect to AB terminals. What is VTH and RTH? Let's find it. Very simple problem. Okay. VTH, let us find. This is VTH. 0. VTH. VTH calculation 1 by 5. 1 by 5. I'm directly using inspection Anna. 10 by 5. 1 ampere is entering plus 1. So VTH 2 by 5. 3. VTH is equal to 15 by 2, nothing but 7.5 volts. Now RTH can be determined. The procedure for RTH, method 1. RTH is equal to VOC by ISC. What is ISC here? So this is VOC, right? What is ISC? You have to short the terminals. When you short the terminals, it becomes like this. The network becomes like this. I'm just drawing the network. Okay? Like this. Now you are connecting a short circuit here. This is ISC. This is 5 ohm. Okay? 5 ohm. And here, if you take 0, yeah, obviously this is shorted. The node voltage will also become 0. Yes or no? Okay. Then, what is ISC? Current through short circuit, how do you find? Once you short, this is gone completely. So this is the only current which is coming, irrespective of this voltage source value. The current all the time flowing in this path is 1 ampere. And the current flowing in this path, because if it is 0, this voltage will become what? 10 volts. And this is already 0. Therefore, 10 minus 0 by 5, 2 amperes is flowing in this direction. This is 2 ampere. This is 2 ampere. This is 1 ampere. This is neglected. Total current is flowing here. How much? 3 ampere. This is what the current flowing here. So ISC is 3 amperes. Then RTH will become what? VOC by ISC. What is VOC? 7.5 by 3. 2.5 ohms. Okay. This is how you can find method 1. Then method 2 also let me try here. Let me try. Old-time technique. According to old-time method, we have to suppress all independent sources. Independent energy sources must be suppressed. That's nothing but 0. When this is suppressed, what is happening is open. When it is open, dependent source is also gone out. Yes or no? So in the resulting network, there is no dependent source at all. And you also suppress this. That means replaced by short. So finally, what is left over? This is open. This is also gone. This is shorted. And finally, you got 5 and 5 with respect to AB terminals. Okay. So it's something like this. Okay. This is something like this. This is the AB terminals. This is 5 ohm and this is 5 ohm. Okay. With respect to AB terminals, how these two are connected? Obviously parallel, and this is completely neglected because open. So RAB or RTH, whatever you get here, 5 parallel 5, nothing but 2.5 ohm. You got the same answer in the earlier case. Okay. So please note down quickly. Meanwhile, I just note down another problem here. Please note down. Question number 16. Please complete that part. I am just noting down another problem meanwhile. This question was also asked in GATE. Is asking what is VTH and RTH. Okay. This is the problem given. 16th problem. Hope you're done with 15th. Okay. I'm just taking this off. Now let us work out that VTH and RTH in this case. Okay. So how do you do it? VTH of 1 by 1 plus 1 by 1 plus 1 by 2, yes or no? Inspection plus 2 ampere plus 2I by 1, equation 1. You already know that I is equal to VTH by 1. Second equation. I is equal to VTH by 1. Right. So substitute that here, then finally you get a VTH value. I give the answer here. You are supposed to get 4 volts. You can find RTH. But to find RTH, when there is an independent source, you got 2 methods. Okay. What is the method 1? Method 1 is formula. RTH is equal to VOC by ISC. So let's find, okay, just by short circuiting the terminals. If you short circuit these terminals, please draw the network again, okay? I have an option here to, without drawing, I'm doing it, but you are supposed to do in the next step. Please draw the network again, okay? So this is what ISC. So as soon as you short it, what will happen? Okay, let me draw it otherwise. Okay, let me draw it otherwise. Better we have a clarity in this, okay? Let me take this particular problem off, okay? I think all of you noted down. I'm just drawing the network again quickly here. All of you can note on that meanwhile. Right. If you want to find ISC according to the first method, this is gone completely. Okay. This is gone. Reason shorted. All are connected in parallel. The voltage across this 2 ohm is 0. The voltage across this 2 ohm is 0. Therefore, current will also become 0. If current is 0, this will become also 0. 2I, right? Yes, sir. When 2I is 0, this is acting like what? Short circuit. Because voltage 0 refers to what? Short circuit, obviously. Voltage 0 refers to short circuit. Then finally, what is left over here? If this is shorted completely, this is gone, this is gone. Then finally, this 1 ohm is parallel to current source, parallel to short circuit. Therefore, what is happening here? This entire current is passing through the short circuit only. That is 2 amperes. So therefore, RTH now will become VOC by ISC, that you already know VOC here, right? What is the value VOC? 4 volts. What is the current? 2 ampere. Therefore, 2 ohm. That's it. Okay. But I want to do it even using method 2 because I want to have a practice. Okay. Okay. Yes or no, all of you? We all should have a practice of calculating Thevenin's equivalent resistance even using old-time technique. What is the old-time technique? Suppress all independent sources. Independent energy sources must be 0. Okay. The resulting network is assumed to be passive. Hope all you remember. Plus minus. What is this? 2I. This is open Anna because I'm suppressing all independent sources. Now I am taking here, okay, this is a network, right? 1 ohm, this is also 1 ohm, and this is 2 ohm. Now let me connect according to the old-time technique. The source I'm connecting with the value of V, delivering some current I. Okay, so what will I get here? V of. So I cannot really say this is I. This should be I dash. Let us take is V dash because already I is defined in the network. Yes or no? Okay. Therefore, when I is defined, let us take some other variable here, I dash, and then V dash. Say this is V dash, and this is already I value, right? I is there already. I given. Now let me tell you here. V of 1 by 1 plus 1 by 1 plus 1 by 2. Okay. Entering current plus I dash plus 2I by 1. Okay, plus 2I by 1. So let me just do the calculation here. This is the first equation. Anna. What about the second equation? I dash is equal to V dash by 1. If you substitute here, what do you get here? This is V dash, okay? V dash. So 1 plus 1, 2, 2.5, 2.5. It's already, okay, 2 plus half. And this is V dash by 1. That means minus 1 when you substitute it here. Then, because when you get here V dash by 1 and you bring this side, and finally, I'm sorry here I, right? Okay, I is equal to V dash by 1. I is equal to V dash by 1. So what will happen when I is equal to V dash by 1? I is equal to V dash by 1, you will get 2, right? This is 2. And finally you get here I dash. So these two gone, then finally V dash is equal to 2 times I dash. It's very clear. RTH. This is nothing but what? RTH. 2 ohm. Please note down all of you quickly. Note down that all of you. So this is how you are supposed to solve the problems. Okay, dependent source, you must be always maximum power transfer theorem. It's very, very important. See, after completion of this entire part, we will try to do some additional problems. At the end of this chapter, we will do additional problems. We pick all high level questions which were asked in GATE. Okay, so far, whatever the questions were there, we will discuss only the important and standard questions. Okay, complete that, I think, all of you. Let's have a look at maximum power transfer theorem. Hope you're done with this, right? Go step by step. There is no hurry. I'm telling you, when you are a beginner, you must learn step by step. I'm telling you. Okay. So most of the students in the exam, they are losing the marks because of, the calculation mistakes. So my dear students, you must be careful all the time. Many times we are observing after completion of the exam, students reach us and share their views. Sir, I have done this silly mistakes. I have done that silly mistake. Only calculation mistakes. They're very good at, procedures and concepts and all. But they do all of a sudden in that 3 hours, anxiety and under pressure. There are sometimes, when you do not have proper practice in the, subject, I'm sure that you commit a lot of mistakes. Okay, be careful, and there is no hurry. Actually, 3 hours valuable time is given. 3 hours span, 65 questions. 65 questions, 180 minutes, approximately 3 minutes is given for each question. So not a simple thing there is. Okay, the GATE exam is something different from other exam, I'm telling you. You can observe generally 100 questions, 100 minutes, 50 questions, 50 minutes. But you never come across, 65 questions, 180 minutes. So in that 1 mark questions, most of them are done, or can be done easily with 1 minute or 1.5 minutes. So the time which you save in case of one mark questions, you can again add that to 2 mark questions or difficult level questions. So what will happen? The difficult level questions or medium level questions are getting, approximately 4 to 4.5 minutes for each question. You understand? Whatever you are saving there in the case of one mark questions, okay, you can add the time or utilize the time in the case of difficult level questions or mediocre level questions. So be careful, I'm telling you. Don't commit to any silly mistakes. Okay, now let's start with important topic, maximum power transfer theorem. There are many questions asked so far in the competitive exams, maximum power transfer theorem. Okay, see, the main objective of maximum power transfer theorem is this point is very important, I'm telling you. And based on this point only, the questions are coming nowadays. Okay, not simple questions. Okay, some logically they're asking, but that logical questions can be done or can be solved easily based on this important point. The statement of the maximum power transfer theorem or the objective of the maximum power transfer theorem you must understand first. Okay, look at this. All of you write that. First you write that particular point. Objective. The objective is to transfer. The object of this theorem, okay, if you can see, is to transfer maximum power to the load by varying the load. Very, very important point. By varying the load. See this. Okay. You want to send maximum power to the load by varying the load. That is the objective in case of maximum power transfer theorem. You want to transfer maximum power to the load by varying some other element. No, that does not come under maximum power transfer theorem. That's not the objective in the maximum power transfer theorem. Understand all of you? Okay, that we do not know what is that exactly. I repeat once again, be careful when you see the problem. In the problem, if you come across maximum power, does not mean that all problems come under maximum power transfer theorem. Understand? What is the condition? Tell me all of you. What is the objective? Tell me all of you here. It is to transfer maximum power to the load by varying the load itself. Okay, by varying the load, you have to send maximum power to the load only. Not by varying something else, you want to transfer the load to the, you want to transfer maximum power to the load. That does not come under maximum power transfer. Okay, this is very, very important. Okay, that means in maximum power transfer theorem, that means in maximum power transfer theorem, okay, the load must be variable. The load must be variable. The load must be variable. That means you are varying the load and then you are transferring power to the load, maximum power to the load. Okay, I hope you understand the point here. Okay, this is very, very important. But the loads are many types. but the loads are, okay, many types. What are the loads? Tell me, all of you. Load, how it looks like? Tell me. You have a source, let us say. Any linear bilet network can be replaced by an equivalent practical voltage source, nothing but Thevenin's equivalent. You give me any network with respect to what? Load terminals. So what is this load? What is this load? Now what is your objective? Vary the load and send the maximum power to the load. Yes or no? This is the load. What is the load? How many types are there? It might be a resistor. It might be a voltage source. It might be a current source. It might be any other circuit also, or any other network also, which consists of a variable. Definitely there should be a variable again. You have a network. The load is a network where you have again group of elements. In that group of elements, at least one element must be a variable. Then only the load is variable. Yes or no? See, in the network, the group of elements. How can you say the network is variable? When any one of the elements is variable in that particular network, you can say that entire network is variable. When the network is load, then load is a variable. Understand all of you? Okay. So it's very clear. Now resistor it might be. Many of the times we remember the formulas when the load is resistor. Okay. But nowadays in the exam, he is giving different loads. Sometimes he is giving voltage source. Sometimes he is giving current source. Okay. Sometimes he is giving a circuit and keeping one variable element in that circuit, and he is asking what is the maximum power transfer condition. Understand all of you? Okay. So be careful. The loads are many types. How many types of loads are there? The loads might be a resistor or a voltage source or a current source or any circuit or network. Understand all of you? Okay. But what is the condition in maximum power transfer theorem? If you want to apply maximum power transfer to theorem to any particular circuit, definitely the load must be variable. What is the load? It might be a resistor or voltage source or current source or any other circuit. So very, very important point to be observed. Okay. So that is why we take one after other cases. I think you have written this, right? Okay. We'll take now case 1. Case 1. What is the first case? Let me take resistor, then voltage source, then current source. Based on this, I will generalize now when any network or circuit is given as a load and it consists of a variable. Now I generalize. Yes or no, all of you? Okay. So look at this. First one. Case 1. Case 1. When load is a resistor. Okay. This is a variable. Now let us see. Any linear bilet network can be replaced by Thevenin's equivalent resistance, yes or no, in series with Thevenin's equivalent voltage. So I can replace any given network. You give me any network, okay, any network, linear bilateral network, that can be replaced by what? With respect to load terminals, that can be replaced by what? If this is a load, okay, it can be replaced by what? An equivalent Thevenin's, okay, Thevenin's equivalent here. So this is A, this is B, load terminals. A, B terminals are always taken as what? Load terminals here. So let me take a load resistor. And what is the condition? It must be always variable. What is the current here? IL. What is the voltage here? VL. Yes or no? Okay, well. Now if you observe, the power transferred to the load will be expressed as IL square RL and also VL square by RL. Okay, now I want to draw a graph. What is the graph? RL is taken on x-axis, PL is taken on y-axis. Then I want to see when RL is 0, what will happen? When RL is infinity, what will happen to the power? Let me check once. Okay. Now, if RL is 0, what is the power? PL, Nana? What is PL? When RL is 0, what is PL? When RL is infinity, what is the power? You understand, all of you? Okay. When RL is 0, this formula gives it is 0. Okay. I'm sorry, here this is divided by, right? Okay. By RL. But this formula gives what? It looks like infinity. When RL is infinity, this formula gives infinity, this formula gives 0. Actually, to check the power for these two conditions, these two are not suitable formulas. You're supposed to take VL into IL is a formula. Power of the load is nothing but its voltage into its current. That's it. Now you substitute RL 0. RL 0 means what? RL 0 means what? VL 0. When VL 0, the whole power is 0. That's it. 0. 0 watt. Now when RL is infinity, infinity means what? Open. When open, then IL is 0. When IL is 0, the product will become 0. Again, 0 watt. Hope you understand. Okay. So when RL is 0, the power is 0. Transfer to the load. When RL is infinity, then also the power transfer to the load 0. I think you might have studied in open circuit test and short circuit test in the case of transformer or DC machine. You might have done. Okay. Most of the people, even EC or triple or instrumentation, anybody will do the experiments in the laboratory. In the case of short circuit test, the load is shorted. So what is the power transfer to the load? 0 only. Whatever the wattmeter reading is observed in the laboratory, that is meeting the losses. That is actually displaying the losses. Similarly, open circuit test also. In the case of short circuit test, the wattmeter reading is considered to be the copper losses, variable losses. In case of open circuit test, okay, nothing but RL is equal to infinity. Okay, the wattmeter reading is considered to be constant losses or else iron losses. Yes or no, all of you? Okay. So that is why the power cannot be transferred when the load is either infinite resistance or zero resistance. It's not possible at all. So that is why this formula is very important. Okay, to draw this graph. So the power is 0 here. This is also 0, but in between it is something like this. Okay, it goes like this. The power reaches maximum when RL is equal to RTH, that is internal resistance of the source. Here in this context, for any circuit, you call that internal resistance of the source as what? Thevenin's equivalent resistance. At Thevenin's equivalent resistance, the power will become maximum. You call this PL max. So therefore, if RL is equal to RTH, okay, then PL will become PL max. PL will become, what is this? PL max. Hope you understand this. Okay. Now, we will prove it. How do you actually prove that when RL is equal to RTH, then PL is becoming PL max? And what is that PL max value also we will see. Okay, I'll give you time. First, you please check because I'm going to generalize the same thing for every case. This is a simple case, but we need to generalize or apply the same case with other cases also. Okay, look at this. When PL is calculated, what is the formula? IL square into RL. But what is IL Nana here? IL is nothing but what? VTH by RTH plus RL. Because I need to express this power because my objective is to find the condition for maximum power and also maximum power value. When you are maximizing or minimizing any given function, what is the general procedure? Suppose f is a function, f of x is a function, x is a variable. Yes or no, all of you? Okay. F of x, if it is to be maximized or minimized, this entire function should be expressed in terms of only one variable. There should not be multiple variables. For example, PL, if you look at, it is IL and RL. Actually, RL is variable. But when RL is variable, you know that current is also variable. That means RL as well as IL both are variable. When the function is having multiple variables, okay, finding the maxima or minima condition with respect to a particular variable will be a difficult task. Okay, or impossible task. That is why what we do is we try to express that function only in terms of this x and the remaining are constants. Okay, so if you see now IL, can I express IL in terms of VTH by RTH plus RL? So what will happen if IL is expressed in VTH and RTH RL? Only RL is variable, no VTH and RTH RL, no variables. Definitely VTH and RTH, are they really variables? No. We already discussed this point in the case of Thevenin's and Norton's theorems. Thevenin's and Norton's equivalents are independent of load value, but dependent on load terminals. This point we clearly mentioned. Okay, independent of load value, but dependent on the load terminals. If you change the load value, they won't change. But if you change the load terminals, they definitely change. Understand? Therefore, here, if I express VTH by RTH plus RL whole square into RL, then dPL by, why dPL, Nana? Because I'm looking for what? Maxima condition. Any maxima or minima condition, first derivative of that particular function should be made 0. Therefore, I'm just differentiating this PL with respect to RL. Okay? Then if I make it 0, then I'll get a condition. If you differentiate this entire part, please do that. You are good at differentiation, I know very well. Okay, you do that part. Okay? So therefore, RL is equal to, you're going to get this condition. This is called condition for maximum power. Condition for maximum power. Understand? Okay, I think all of you understand this part. Okay, you are differentiating this particular part and making it 0. Then you will get RL is equal to RTH. So you do that differentiation part. You please take care of that. Now, once you apply this condition here, if I make RL is equal to RTH here, this entire circuit is said to be, okay, maximum power transfer condition circuit. Okay, the circuit is now corresponding to the maximum power transfer condition. Okay, or else if you apply the same thing in this formula, then you will get PL max is nothing but, if you apply here, then you will get VTH square by 4 times RTH. So call it equation 1 and substitute. Okay, this is 2, let us say. Now substitute equation 2 in 1, then you will get, okay, this is what the formula. Understand all of you? Okay, so first you please note down this, then I will go with the other cases. But before that, okay, before that, please, all of you, just wait for a minute. Just wait for a minute. Look at this, all of you. What is the observation? Okay, what is the observation? The power is increasing up to RTH, then it is decreasing. Okay, so I can write that when RL is increasing, for all RL less than RTH, for all RL less than RTH, when RL is increasing, PL is increasing. For all RL greater than RTH, what is happening? When RL is increasing, PL is decreasing. For RL is equal to RTH, okay, what is happening? PL is becoming PL max. Yes or no? This is very, very important observation. That's it. Please note down, all of you. I give you 2 minutes time here. Please note down. You completed this part, okay? So remember one important point to be observed. Your objective is to optimize this power. That means maximize in this particular case. Optimize means maximize or minimize. But in this context, what is the title? Maximum power transfer. So we are looking for maximization. Our objective is to maximize the power. Maximization of any particular function. This is a function, right? Okay, power is a function of what? RL now. It should be function of RL. It should not be function of any other variable. Okay, so the fundamental concept is that whenever a problem is given, whether it is a resistor or voltage source or current source or any other circuit sometimes, what is actually the fundamental principle of maximum power transfer theorem when you're trying to obtain maximum power transfer condition, you must always remember this particular point. That power must be always expressed in terms of the variable, whichever the variable is given. That variable might be a resistor according to this, or voltage source or current source, or any variable in the given circuit, anything it might be. So that power must be a function of variable, and there should not be any other variable, remember all of you. Okay. Now I try to do the same thing. Look at this. This is a variable, this is a variable. What did I do here? IL is expressed in terms of VTH by RTH plus RL, where now VTH is constant. We know that VTH is independent of load value. RTH is independent of load value. Now this entire expression is a constant value or not? Yes. Now where is the variable? This is the only variable. Of course, this is a variable, no doubt. But VTH and RTH are also constants here. Now this entire power is expressed in terms of only one variable. Got it? Now you differentiate this power with respect to that variable and make it 0. You get a condition for maximum power transfer. I'm stressing upon all this, for a reason. Nowadays the questions are coming in a different manner, only based upon the derivation of maximum power transfer condition. This is a derivation for maximum power transfer condition. Understand? Okay. Now we will take a different load, case 2. Please write down that, case 2. Case 2. What is the case 2? Let us take voltage source. Yes, we can take voltage source. So what is the load? Actually, you call it load must absorb the power. Yes or no? Any load, whether it is a voltage source or current source or any other circuit or resistor, definitely the load must absorb the power. So to absorb the power, the load for a given current direction IL, what must be the polarities of the voltage source? Definitely like this. Then only it is said to be absorbing the power. So therefore, this is VL. Now VL is variable. Yes or no? Now VL is variable. What is the maximum power transfer condition? Condition. What is the condition that we mentioned? The load must be variable. Okay. So therefore, now we'll see PL is equal to VL into IL. But there are two variables. When VL is varying, we know that IL is nothing but VTH minus VL by RTH. When VL is changing, IL will also change. According to the discussion we had just now a little while ago, there should not be many variables or multiple variables, only one variable. But we express this current, because VL is a variable, but express this IL in terms of other things, other constants here in the given circuit. Can I write IL is equal to VTH minus VL by RTH? Yes, I can write. Yes or no? That's it. So now let us take dPL by dRL. Yes or no? This is the first equation. Is equal to 0. What will happen? VL into VTH by RTH. Okay, I'm sorry. This is VL, right? Variable is nothing but what? VL. Now VL, then you get what? VTH by RTH minus VL square by RTH. Then it becomes what? 2VL by RTH is equal to 0. Now you get VL is equal to VTH by 2. This is called condition for maximum power transfer. Understand? This is what? Condition for maximum power transfer. If you substitute this one here, you will get PL max is equal to VTH square by 4 times RT. That's it. So condition for maximum power transfer and maximum power value. Please note down.